Now, 1D problem is, we're talking about 1D problem, okay, class. So 1D problem is characterized by only one coordinates, then it can only represent the problem that we want to solve. So the characteristics of 1D problem is there is one coordinate system where the dimensions of the elastic body is very large in that directions compared to the other two coordinate direction, which is perpendicular to that directions. So one very typical classic, one very classical problem under 1D problems that I cover in class is the bar problem. Okay, bar problem. So remember, there's another 1D problem also that we didn't cover, which is beam. Beam is also considered as 1D problem. Okay. Now, if we look at bar problem, so the characteristic of the bar problem is we have one bar, then there are two ends here. And this is represented, as I mentioned, using one coordinate system. And in general, the bar can also change in, the bar can change in the sectional, the area of the cross section, it can change. Okay, and then we have only one displacement, which is non-zero. So displacement only one. Stress also only one in x direction, the other all zero. And the strain also one. Okay. And the equilibrium equations that we need, because we need only one equilibrium equations in x directions. We need only one stress-strain relations. And we need only one strain displacement relations. So three variables that we need to solve, unknown variables of the problem, and three these basic relations. And of course, don't forget, we always have boundary conditions. So class, when we come to boundary conditions, remember there are two types of boundary conditions. One is related to displacement, and the other one related to stress, or it is called natural boundary conditions, geometric boundary conditions, or kinematic boundary conditions. The boundary condition is what happened for the bar problem here when x is equal to 0 and x is equal to the other n, which is, let's say, dimension is given to L. So boundary conditions here means at x is equal to 0, or at x is equal to L, x is equal to 0, x is equal to L, x is equal to 0 is this n. If your x is starting from here, means this n here. So either there are two n's only. So x is equal to 0, x is equal to L. What is the value of known displacement? So the displacement must be known, yeah? What is the displacement? And for stress, so this will be what is the stress, which is known. At x is equal to 0 or x is equal to L. So it must be known. Yeah? It must be known. Okay. The same thing here for displacement will be what is the displacement, which is known. It must be known. So we have two ends. So there are two boundary conditions. There are two boundary conditions. So the boundary conditions can either be displacement or stress. But remember, one end can only have one boundary conditions, either displacement or either stress. Either displacement or stress, cannot have both. Okay? So if this is displacement boundary condition, for example, here fixed, then that is only boundary condition. Then we come to the next one. Here is free. Is it free? Then that means the displacement is unknown. So we are looking for the known one. So here, if there is no force applied here, so we know that this stress is zero. Stress must be zero at this free end if there is no point load applied here. So this we apply the stress boundary conditions. So we have to know what happened to at the end there, especially do we know the displacement, or we don't know the displacement, or do we know what is the stress there, or we don't know what is the stress there. So that is the thing which we need to take note of, boundary conditions. So some of you make mistake in the boundary conditions in the test that I have given to you. So you have to try to look back. I think boundary conditions will be either the displacement or stress. If you have here fixed, here also fixed, then that means displacement here zero, displacement here also zero. So both boundary conditions, either here and here, they are both related to displacement, because displacement are known here to be zero, displacement known here must be zero because these are fixed. But if this is not fixed and there is a point load here, if it is not fixed and there's a point load here, then here this is free end, and under this loading, this bar elongate displacement, we don't know. So what we know will be the stress at this end here. So when we draw a free body diagram here, this is the force applied there. This is the traction, the resultant of the traction applied there. Then we have stresses just at the boundary there. So this is a sigma x just at the boundary there, and we multiply with A, then we get the resultant force, and this must be equal to this. So the boundary conditions here will be sigma. From here we can derive x is equal to L is equal to P bar. So sigma x, the boundary condition, stress boundary condition is what is the stress at this end that we know. So the boundary conditions will be A at this end here. At this end for this problem, x is equal to 0. So this is at x is equal to L. This is a boundary condition, and for this problem, x is equal to 0, u is equal to 0. Okay. And later we see we have to relate this to u. We have to relate this to u. So for 1D problem, sigma x is equal to E epsilon x from the stress strain relations, and for the strain displacement relations, we have this is equal to this. So stress can be related to displacement u by these relations. So if we substitute here into here, for E, assuming E they're all constant here, so we will have E du dx, and this must be the value at x is equal to L equal to this over A. Equal to this over A. So here, that's why we can get, if E is constant, if the problem here E is constant, so we have du dx. When x is equal to L, it's equal to P bar over EA will be the boundary conditions when x is equal to L. And together with another boundary conditions, then if we integrate the governing differential equation for this, then we can solve this. So that is the problems, how we define the problem of a 1D problem. Now, typically when we want to solve for 1D problems, we need to have what we call governing differential equation. From theory of elasticity, we need to get the equilibrium equation considering one small part of this. Considering one small part of this. Okay. So that is what I want to go next. Okay. So I hope everyone can hear, okay, because I get the message that somebody has left the chat. So is there any problem with the internet? Okay. Sorry, I think just now Amir Rushdie and Kasim, you were not able to join. Yeah, sorry. Are you okay now? So now let me answer the questions of, sorry, just now you are waiting in the lobby for quite a while, and then you are in the lobby, there is no coffee, okay, for you to drink, okay. Now, let me go to, now it's 4:30, let me go to the questions by Ahmed. Now, class, if you have any questions, I think you have to type in the chat, okay? Because I cannot hear if you talk. Okay, sorry. So I hope the connection is reconnected now. You are reconnected now, yeah? Now, let me talk a little bit on, because I still want to talk a little bit on the energy method. So let me finish off this with the governing differential equations, okay? Now, governing differential equations is equations that we use to represent a problem. In 3D elasticity, it is in the form of differential equations. And this is obtained by considering one small part of the, can't see the whiteboard, yeah? All of you can see the whiteboard or no? The rest of the, Amir Rushdie, you can't see the whiteboard? Yes, let me. And what about other students? Are you able to see the whiteboard?